Anyways, good afternoon, everybody. Welcome to another exciting afternoon of Chemistry, Chem 170, with your host, me, Dr. White. We got a lot to do, but first, a couple of public service announcements from me, the management, and I am. But anyways, first of all, don't forget tonight at 6 to 7:15 on Zoom, I will have my office hour. If you got any questions about anything, stop by and say hello and ask your question. Next, don't forget, coming up soon, if you want to do it, is the deadline for the extra credit project. Remember, the extra credit project is, yes, 10, 10 extra points. And as I said when I first discussed it, it's on the sheet too. Send me your extra credit project before you upload it. Try and do it in advance, a couple more than just the day before. If there's any problems, I'll let you know so you can fix them. Or you can come to my office hours and discuss that with me, and I'll help you out. That way you can get 10, 10 bonus points. All right, speaking about my hands, did anybody do the not extra credit, the homework project? Did you take your right hand and put it up the mirror and you saw, oh, look, my left hand. And if you want like this, it goes like that in the mirror. But, and remember my famous joke, you know what this is, don't you? A spider doing push ups on a mirror. But, anyways, did you think about things in your daily life? Like if you were putting on your shoes, did you think, are my shoes chiral or achiral? Remember, chiral, something with a non superimposable mirror image, achiral, something with a superimposable mirror image. Now, pro tip, if it has in the description left or right, like my left shoe or right shoe, immediately you know it's chiral because it has handedness. Anybody try and do their superimposable your hands and find out, oh no, nothing lines up because your hands are chiral. All right, now on Monday, I was finishing up with and starting to talk about chiral centers. And a chiral center is a molecule that has four different groups. I can actually expand this definition, or four different atoms, or a combination of four different groups or atoms. And turns out, and I'll explain more today or on Monday, why having a chiral, in our case, carbon, is quite important. But, anyways, chirality or chiral carbon, you have to have four different groups. When that happens, that's considered a chiral center. But since this is organic chemistry, I'll just be talking about chiral carbon atoms, which, being a lazy organic chemist, I shortened down to just carbon atoms. Oh, I forgot to mention, today is International Chem 170 Turn on Your Webcam Day. So make Dr. White happy and turn on your webcam. For those who have, thank you. See, you're making me happy. So don't forget, it's International Turn on Your Chem 170 webcam. Oh, people are doing it. I see real faces. Thank you, Anna. And everybody turn it on. All right, let's go back to chiral centers and chiral carbons. Everybody see my whiteboard? Thumbs up, people. Thank you. All right, now we went through this last time, but I'll do it for you. Everybody see my screen? Oh, I see everybody doing their thumbs up. Thank you. And the question is, circle the chiral carbons. Now, it's time for Dr. White to give you a real good tip. In order to have a chiral carbon, it needs 4 different atoms, 4 different groups, or a combination of 4 different atoms or groups. Oh, wait, can I do this? I can make me bigger. Ha ha, look out. And you're bigger too. All right, now, let me get me smaller. But it has to have 4 different groups or 4 different atoms or a combination of 4 different atoms or groups. Therefore, if you have a carbon with 2 or more of the same group, it can't be chiral. Also, if a carbon is in a double or triple bond, it can't be chiral. Let me say that again. If you have 2 or more of the same atom or group on a carbon, it cannot be chiral. If you have a carbon in a double bond or triple bond with either another carbon or another atom, it can't be chiral. So let me do this one. And the question is, circle the chiral carbons. Oh, look, 3 hydrogens on that, and that's out. 2 hydrogens. Remember, if you have 2 or more, the same atom or group, you can't have 4 different things on a carbon. So this carbon's out, and here again, 3 carbon. I like my sound effects today. And this carbon has 3 hydrogens. That's 2 or more, and that's out. Ooh, that's an awful looking check. That's better. So that leaves us with these 2 carbons to consider. Now, let's look at this carbon right here. It has a hydrogen hydroxyl group, a methyl group, and this I'll call R, all those carbons in a chlorine. So I have hydrogen, hydroxyl, methyl, and R. That's 4. So this is a chiral carbon. Now, let me erase these circles because I was just using that. Now we have this carbon as a methyl group. It has this whole thing I'll call R. Let me get rid of this R. As a chlorine and a hydrogen. And therefore it has 4 different groups or atoms or combination: hydrogen, chlorine, methyl, and what I'll call R. So this would be chiral. And that's how you do it. All right. Oops. This is SH. Let me clean this up. This is a double bond. And why don't you circle all the chiral carbons in that molecule? Like I said, I'm going to share the fun today. Well, I always do. And for those of you who turned off your webcam, turn it back on, please. Somebody who's one of our students knows, oh no, I'm missing the dog with the marker. Well, good news. Since y'all have your cameras on, I can see nobody's got smoke coming out of your ears from being overtaxed by my question. Oh, I see someone's got their answer ready. Unfortunately, unless I unpin everything, I can't see it that well either can everybody else. But thank you, Tom. The dean will be happy. Some of my students like to do that. I don't. Shh, don't tell her I said that. All right. Anybody need more time? Yell out. Okay, let's take a look at B. And the question is circle the chiral carbons, 3 points each. Now, the quick way is look for carbons that can't be chiral. If it has 2 or more of the same group, or if it's in a double or triple bond, it can't be chiral. This one has 3 hydrogens, it's out. Oh, look at these 2 carbons, they're in a double bond, they're out. CH2, 2 or more are the same, it's out. And this carbonyl carbon is double bond to oxygen, that's double bond, that's out. So we just have this, and this carbon to consider. And if we look at the first one, this one, we have a hydrogen, a thiol group, a methyl, and then all this, and it's all different. So that would be a chiral carbon. Come on, eraser. All right, why is my eraser not wanting to erase? That's weird. All right, hold on 1 second while I do something. Let's see if this will help. For those of you who don't know about CCleaner, hopefully, let's see if that helped. All right, I'm going to shut this down and bring her back up again. Or better yet, I'll just do different colors, then I'll shut it down. If we look at this carbon, sorry about that, technical difficulty, I don't know why. It's been good to me all semester. All right, this carbon has hydrogen, bromine, this whole group here, and this whole group here. It's different. 1, 2, 3, 4 different atoms or groups of atoms or molecule or groups of atoms, and therefore that's chiral. And finally, let's look at this carbon right here, and that shouldn't be a 2. Sorry about that. And you have a hydroxyl group, hydrogen, this carbonyl with the hydrogen, and this whole thing right here. And those are different. 1, 2, hydroxyl group, 3, hydrogen, 4. Therefore, that would be chiral. And that's how you do it. But before we go forward, let me close this. Let me open it again. And now it's working again. Don't ask me why it freezes up. I think one of the more complex structures I draw. But anyways, we're back on track. All right, let's do one more. Again, the question is circle all the chiral carbons. Does everybody see the ring on your screen? Think about it. 6 months ago, if I said, do you see the ring on your screen? Would you know what I was talking about? Think how much you've learned, and you should all be proud of that. Oh, I'll give you a hint. Remember, 4 bonds to carbon. Is today Friday the 13th? Wait, Friday the 13th has been lucky for me. Is today Wednesday the 24th? Oh no, that's why I'm having problems. Part of it is I've got so many things going on this computer with the tablet, Zoom, my webcam, and everything else. Sometimes it will freeze up like that for one of the applications. I know if I just log off and log back on and use CCleaner, it always clears it up. All right, anybody need more time? Thumbs up, people. If you're done, give me thumbs up. All right, the thumbs have it. Thank you, thumbs up, people. All right, now let's take a look at the ring. And before I do, let's show the hydrogens. This carbon has 2, because there's 1, 2 bonds. There should be 4. 4 minus 2 is 2. This one has 2. This one has 1. This one has 1. And this one has 1. Now, as I taught you, the quick trick is if a carbon has 2 or more of the same group, it's out. 1, 2, that's out. And this one is out. 2 hydrogens, 3. But that leaves us 3 carbons to go, which this one, and this one. And if you look at this one right here, it's got a hydrogen, chlorine, this part of the ring, and this part of the ring, which are different. So it has 4 different groups, and therefore I'm going to circle it because that's chiral. And if you look at the next carbon next to it, this one, the same thing. It's got a hydrogen hydroxyl group, and let me get rid of my little dots here. Oh no, I wiped out a hydrogen. Now, if we're looking at this carbon right here, it has a hydroxyl group of hydrogen. These 2 carbons with a chlorine, and these 3 carbons right here, 2 carbons in a ring. And those are different. Therefore, this is chiral. And finally, this last carbon, same thing, methyl, hydrogen, and then these 2 carbons of the ring and these 2 carbons with hydroxyl. So this would be, and therefore you have 3 carbon in the molecule with a chiral center. Oops, not what I wanted. Now my software would write glucose, which this is what the molecule is. I'm writing. And remember, this is by definition equivalent to, that's what the third identical to this. So in glucose, one more time, everybody, circle the chiral carbons. Now, every intersection of the line here is really a carbon. So there's a carbon here, 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 and here. Oh, it makes my heart beat so nicely to see and feel good. See all of you working on where the chiral carbons. Thank you. It's called positive reinforcement, and it works. When you're done, give me a thumbs up. For those who don't have your webcam on, you can use your emoji. But remember, I think it was in this class that I changed the name of emojis. I'm going to call it Symboli. Uh-oh, it's Terrible Humor Wednesday. All right, I think everybody's done. Let's take a look at this. If I look at this carbon right here, notice it has two hydrogens, so it's out. This carbon here, which is really this carbon here, is involved in a double bond, so it's out. And what that leaves me with is this carbon right here, hydroxyl hydrogen, the aldehyde, and the rest of the carbons, it's chiral. This carbon right here, hydrogen hydroxyl group, these two carbons up here, the other carbons down here, 4 different groups, it's chiral, and then these two also. And glucose has 4 chiral carbons. And in order to have a chiral molecule, you need at least 1 chiral carbon. If you don't, it's not going to be chiral. Now, something I haven't really talked about, and the switch is off for this definition, but it's something I'll be discussing in a little while, so you'll need to know. There's something called stereoisomers. Those are isomers. Now, an isomer is different molecules that have the same molecular but different, can have different structural, but a stereoisomer are isomers that have the same molecular and the same structural formulas, but different in their orientation of atoms in space. That's why it's called stereo. 3 dimensions, stereo. Now, isomers whose, another way of saying that is isomers whose atoms are connected in the same way, but differ in their arrangements in space. And that's the stereoisomer, and that's the whole concept is called stereoisomerism. Aren't you glad I'm not doing enunciation quizzes? Oh, I could do that online. Turn on your mic and say this word. No, I knew a faculty member who did that in general chemistry, made his students name certain things and know how to pronounce them. Now, for stereoisomers, major feature is a chiral center. And that's because you have a rigid structure. Nitrogen, if you look at a quaternary ammonium salt, again, I'm never going to ask you what are the major features of stereoisomerism, but have you ever had an umbrella and you're in a rainstorm and it flips? So instead of going like this, it goes whoop. That's happened to me. I'm sure it's happened to you. Well, nitrogen in a quaternary ammonium salt can have 4 different groups, but it can go up and down, and therefore it's not rigid and it can't have Guess what? Stereoisomers. Now, if you remember, it's show and tell time. By the way, did anybody happen to wash your hands since we last met? I hope you all did. That'd be pretty funky if you didn't, especially in our COVID-19 environment. Did you think about making micelles? Anyways, back to here. These are two different molecules. They're identical. This carbon has a black, a silver, a yellow, and a red. So does this, but they're not identical because they're not superimposable. And these are stereoisomers. And turns out a lot of molecules in your body and nature are stereoisomers or one isomer, and it makes a big difference. I'll talk more about that. Now, switch is on. Big time. Hold on. It's Subtle Wednesday. Aren't you glad I don't expect you to be able to read my mind? And that's enantiomers. Now, what is an enantiomer? A molecule with a non-superimposable mirror image. And we have what's called enantiomeric pairs. And if I were to ask you, draw the enantiomer of glucose, and let me switch to my whiteboard. I'll never ask you to memorize the molecule glucose, but I can give it to you on a test. Wrong thing. Right thing. Wrong color. Hopefully I spelled enantiomer right. I sometimes spell it wrong. Anyways, if there's a spelling error, you'll know why. SP is spelling error. All right, so let's look at this. All right, if I give you this and I'd show you this structure and I ask 3 points each, draw the enantiomer for that, what am I really asking? I'm asking you to draw the mirror image. Well, how do you do that? Now, you don't have to do what I'm going to do, but I like for a mnemonic device for my memory and brain to put in my mirror like this. This is my mirror. Now, you don't have to do this, but it helps me. Now, if you take and hold this molecule up to the mirror, you're going to see a reflection. Now, an aldehyde, since it has an achiral carbon, it's not chiral. I can just draw it like this. I don't have to worry about a mirror image. Same thing right here, this carbon. Now, I'll give you a second or two to get it all written down, what I've done so far. And I'll get to look at everybody's faces. Hi, everybody. Oh, Dr. White's so happy. Thank you for turning on my, see how easily I'm pleased? That and talking about organic chemistry, I'm in a good mood. All right. If you take your hand, and let's assume there's a mirror right in between, and you hold it up to the mirror, you'll see your left hand. Now, when you look, here's the mirror in between. Here's the when I'm looking, here's my hand, here's the image. What do I see first in the image of them in the mirror? What's closest to the mirror? The palm of my hand, I'll see. And that's true with anything. When you hold it up to a mirror like this, I'm going to see the yellow and red in front and the silver and black behind. And that's because what you see in a mirror first, put in the mirror closest, that's what you'll see to reflect. Ooh, do you see my reflection? My right hand? Never mind about the spider. I love that joke. So what does that mean? If we look at, and thumbs up people, do you see my whiteboard on there? If you look at this carbon right here, what's closest to the mirror? Hydroxyl group. That's what you'll see. What's farthest away? Hydrogen. What's closest here? Hydroxyl group. What's farthest away? Hydrogen. What's closest here? By the way, the closer I get to May, the worse my hydrogens look. Do you believe that? Nah, just not doing it well today. What's close to the mirror? Hydrogen. What's farthest away on this carbon? Hydroxyl group. And the last one, what's close to the mirror? Here's my mirror. Hydroxyl group. What's farthest away? Hydrogen. And this is the answer. That's the enantiomer of glucose. It's a non-superimposable mirror image. Now, this is called a Fischer projection. And I'll teach you later today or Monday why, when you're doing, is this superimposable or not, Fischer projections, you can only pick up and lay on top of another Fischer projection. You can't rotate it to see if it's superimposable. Let me say that again. Fischer projections and their mirror images, you can just pick one up and lay it over the other. You can't rotate it to see if it's superimposable. And therefore, this is superimposable on there, and therefore it truly is the enantiomer.
So, quick question.
You're so if we... didn't do it quick enough.
Okay. Go ahead. So would this actually be OHC for the second one instead of if it's the mirror, or does that?
Which one are you talking about?
The very top, the CHO.
Well, you could write the mirror like this.
Yeah, that's.
But since it's a achiral carbon, it's going to be superimposable on its mirror image. It doesn't. This. One of the things I haven't mentioned. Ooh, this is a good time.
So I mean, I'm just saying the reason I'm asking.
There's a reason why you're asking a question, which I neglect to talk about. Have you ever gotten some of those things where you assume everybody knows what you're talking about because everybody in your world knows that? Well, you don't. All right, let's assume I have bond between two carbons right here. This black and this black is a carbon. This is a carbon-carbon single bond. There's free rotation around it.
Yeah.
So the one here can rotate around, and because it's a chiral, it doesn't matter which way you draw it. Now, if you want to draw it as a mirror image, go right ahead, because I'll mark it okay. But I'm a lazy organic chemist, and if we don't, we don't.
I just didn't know if there would be a hydrogen bond going up to the oxygen.
Well, it's on there, but we're only looking at carbons.
Okay.
All right.
Sorry.
There's nothing to be sorry about. Remember, in my class, there's no such thing as a dumb question ever. Okay? Ooh, Dr. Wake got serious there. Look out. But I am serious about that. All right. It's time for you to have some fun. I don't know if this is a real molecule or not, but it's something for you to have fun with. And the question is, draw the enantiomer. 3 points each. Have fun. Oh my goodness, I get to see all my friendly students out there in Zoom land. What do you call out there in the Zoom meeting? Zoomlandier? Get to see most of you have a neater place than my office. It's a never-ending battle to keep it clean. In fact, this weekend I'll go to war with my office again, do a cleaning, and within a month it will be a mess again. Not a mess, but. And when you're done, give me a thumbs up. All right, I think everybody's got their thumbs up almost. Everybody does. Let's do it. So what does it mean? Draw the enantiomer. Means draw the mirror image. And it'll be non-superposable. I'll never give you something where there's no enantiomer. I'll say that in a second. So first of all, I'm going to do my backbone. 1, 2, 3. The bottom here, I have CH2OH. It's achiral. Here I have my aldehyde. So I don't, extra line fell in there. And now here's my mirror. What's closest to the mirror in the first carbon, you'll see first. What's farthest away, you'll see farthest away. Next carbon, what's close to the mirror, hydrogen. What's farthest away, this one. And finally, the last one, what's closest to the mirror, this one. And what's farthest away, this one. And that's how you draw an enantiomer. If you want this weekend, if you happen to be on Zoom with friends or you know people are fully vaccinated that you can be with, you can impress them and show them how to draw enantiomers. People don't like to hear that. But that's an enantiomer. Now, switches off for this. There's another type of stereoisomer, which you learned about, but I didn't want to confuse you with the name at the time, and that's called a diastereomer. And those are stereoisomers whose molecules are not mirror images of each other. An example of that would be sister trans 2-butene I showed you long ago. They're non-superimposable. They're stereoisomers because they differ in how they're connected in space, but I'll never ask this on a test. But if you ever happen to run into anybody talking about diastereomers, you'll know what I'm talking about if you remember this. All right, let's talk about Fischer projections. Before that, I have a sad story to talk about. You've heard me talk about Emil Fischer, great German organic chemist, a great one. Unfortunately, Emil Fischer died way too young. Emil Fischer is the one who figured out how to make esters. It's called Fischer esterification because he discovered that or created it, which is, that alone is a great achievement in organic chemistry. But what he's well known for is his work with sugars. And it killed him. How did it kill him? Well, back in the late 1800s, early 1900s, especially if you're working with sugars, you'd make derivatives. And there were certain derivatives that you would make, which would be solids, and you could get good melting points out of. If we were in the lab, I'd talk more about it. But anyways, they had a bad habit back then. They taste things. You don't do that in the lab. Well, they did. And one of the most important derivatives is reacting 2,4-dinitrophenylhydrazine with a sugar, smaller ones, and you get a nice solid that you can get a very good melting point, and that helps you elucidate, that's a fancy word for figure out the structures. And all the smaller sugars, Emil Fischer figured out. but he died of 2,4-dinitrophenylhydrazine poisoning because not all that would react. He tasted it, and eventually it killed him. Sad but true. But what Emil Fischer figured out, which is also named in his honor, is Fischer projections. Here's a molecule, 3 dimensions. How do I write it in 2 dimensions on a piece of paper, but still showing the 3 dimensions? Switches off for this, but is in other classes you might need to know this. So what you do is, here's my 3 dimensions. Again, switches totally off for the slide, but the black wedge means C is coming towards you. The dashed wedge is going away from you behind the plane of the paper. In the plane of the paper are A and D. And if you rotate this 90 degrees, then flatten it out, you'll find C is on this side, E is here, D is on the bottom, A is up. And what this really means is A and E are coming towards you, and C and E are coming towards you, and A and D are going away. This will not be on a test. But one time I did, and everybody always got it wrong. And I figured, nah, I got better things to talk about than spending a lot of time teaching students how to do this, because you're not going to do this. Now, what I mean by this is, here is the Fischer projection. Yellow's coming towards you. Red is, let's do it this way. Red is coming towards you. Yellow is behind or farther away. And in this plane right here are black and silver. And if I rotate it like this, I'm not going to do it, but smash it flat. Red will be on this side, yellow here, black, silver. And you see it like that. But in reality, it's coming towards you like these. These two are going away. And each carbon in a Fischer projection shows that, even though it's only 2 dimensions. And it was a great, I guess you call it, invention of his that made him even a greater chemist, the work he did. Well, like I said, unfortunately, organic chemistry also killed him. Quick story. For a while, I thought I did myself in. When I was a postdoctoral fellow, I was working with, and I made it myself, high purity ozone. Ozone is extremely dangerous. And I came down where I had this fever, I felt weak, and I didn't know what the heck was. And a couple months earlier at the chemistry department, a student actually destroyed his liver, almost killed himself, part of his liver, by working with chemicals and getting exposed to them. And as careful as I did, I could still smell I was getting some light exposure to ozone. So I went to my doctor, and this went on for a couple of weeks, and I was getting concerned. And this doctor, who was very good but had a bad sense of humor, called me up one day and said, I figured out what's wrong with you. And he said, I need to talk to, actually, the way it went, he got in touch with his office. He needs to talk to me. So I called him and said, I've got good news and bad news for you. And I said, all right, what's the good news? He said, I know what you have. He said, all right, what's the bad news? There's no cure for it. And guess what? I came down with mono, which unfortunately got worse when I had hepatitis. Luckily, in my building, there was a nurse who lived there when I lived in Chicago. And every night for about 6-7 weeks, when she'd come home from her shift, she'd knock on my door and say, open your eyes. And she'd look to see if I'd gone jaundice, yellow, which means you're in serious problem. But anyways, that's what killed Emil Fischer. And this is a Fischer projection. And that's what this means. C and E, like yellow and red, are coming towards you. A and D, like silver and black, are going back behind the paper. And if I look at the clock, I'm going to do something I haven't done all semester, because for some reason, we're a little behind on schedule. Right now, we're on schedule. And on a Wednesday, what I normally do, and if we were face-to-face, is say, all right, let's take a 10-minute break, but today we'll just take a 5-minute break because we're on Zoom, and then we'll do the lab, and today's a quick lab, and I can get you out early. Thank you, Dr. White. You're welcome. So everybody, let's take a 5-minute break. Let's see, it's 10:48. Why don't you come back at 10:48? Wow, did I read it wrong? 1:48. Why don't you come back at 1:55? We'll take a couple minutes and we'll finish lab and we'll be done by 10 after 2, if not earlier. And for those of you who turned on your webcam, thank you, and really thank you. I'll see you in about 6 or so minutes. I'll be back. Time to start. All right, everybody back? So everybody logging in, turning on their webcams, making Dr. White happy. By the way, I fixed up my makeup while we were on break. No, I know. I was wondering, should I get TV makeup? Like, nah. All right, it's lab time. Now we're on schedule. So today's lab, if we were in the lab at ECC, I'd say today's lab, you'll determine is Dr. White lying to you or not. Not, but still in chemistry and science, but especially chemistry, you want to find out if something's the truth, you go into the lab and prove it. And today's lab, you're going to do that if we were there. I'm going to give you the data, but today's lab is light dissolves light. And as you learn, everybody see the lab on the screen now? Thank you, thumbs up, people. In chemistry, there's an important rule of thumb. That means it's not a law. A law is always true. A rule of thumb is mostly true. And it describes that polar substances are soluble in other polar substances, and nonpolar substances are soluble in other nonpolar substances. Now, in our universe or world, water is the most polar substance, period. Water. Now, today's lab, you would be using hexane, which is nonpolar, which is similar to gasoline, which is nonpolar. And in today's lab, you'll determine if various substances are polar or nonpolar. And these are things you use in your daily life or good. And this will be accomplished by determining if these substances and products or whatever you mix together or these compounds are soluble in either water or hexane or maybe both, because it's a rule of thumb, not a law. And if a substance is soluble in water, then it's polar. If a substance is soluble in hexane, then it's nonpolar. And finally, you'll determine, having some fun, if pairs of mixtures of substances created form homogeneous mixture. That's another way of saying IE means that is soluble in each other. And if we were in the lab, I'd tell you hexane is flammable like gasoline. Be careful with it. In an organic chemistry lab, we never light a match or a lighter or a Bunsen burner, instant fire. Now, let's look at the lab. In part one, you take some small test tubes, which you have in your drawer, we're in the lab, and you put about 1 to 2 milliliters of DI water. DI stands for deionized. Your tap water from the sink has a lot of ions in it. How many of you ever heard of hard water or soft water? That's usually how many calcium and other ions there are. And we have cartridges, filters they're called, that remove those ions, and we call that deionized water. And for short, we call that DI water. And any experiment you use DI water. I was working for one company, a group of compounds they made. They needed ultra high purity DI water, and they had some really fancy filters to get that out. It was expensive, but that product was for NASA, and they needed that kind of purity. So you'd put some water in the test tube because we're doing water solubility. You'd put a small amount, like a few drops of whatever you're testing, either a liquid or if it's a solid, a small amount, then you'd mix it. And I teach you the following. By now I would have done this already, but one way to assume this is a small test tube, never ever put your thumb on it and shake it, because you can get chemicals on yourself and people around you like Dr. White. Now, what I teach you would be, if one way is you hold the test tube and you hit it 3 times real good and it mixes up. I would say, don't tickle it, hit it really good, but you got to hold on to it or it goes flying. That mixes it. Now, another thing we have, which is quite fun to use, is a Vibro Mixer. Let's see if I can get a, hold on, we got time. Oh, it's not even midnight yet. I should have looked this up in advance. It's one a few times. I'm just not finding it right now. 2 days later. Well, anyways, time to use your imagination. Imagine a box with a thing coming up with a rubber plate. And when you push down on the test tube, it vibrates real fast. I mean, real fast. And it mixes up the test tube. And those are fun to use too. So all you got to do is go like this, and it goes like this, moves the test tube, and does that. Well, anyways, you would be mixing up these various samples. And you check to see if a solution is homogeneous. Homogeneous means the same. It does not have any layers. And you let this sit for a minute or two, look at it. And if you had any problems, I'd say, call me over and I'd help you. When you're done, put it in the waste speaker. Then you do the other substances, doing the same step with some water, mix it, and see if it's homogeneous, soluble. Now, it turns out, and you don't have to write the structures for this lab. In table 1, I've already given you the data. And notice I have things like acetone, baby oil, ethyl acetate, octane, sodium chloride, starch, sugar, vanillin, Vaseline. Do it in a beaker, not in a test tube, because it's impossible to clean out of a test tube, and vegetable oil. And that would be part 1. Now in part 2, instead of using water, we'd use hexane. And similar to part 1, instead of water, we'd put about 1 or 2 milliliters of hexane in a clean test tube, put a small amount of the liquid or solid in that test tube, mix it properly, and check to see if it forms a homogeneous, that means it's the same throughout, no layers, solution. If it does, then it's soluble. If it doesn't, it's not soluble. And if you notice, I have solubility of hexane observations, and you would do this all in the lab. Again, it's the same compounds: acetone, baby oil, ethanol, alpha acetate, octane, sodium chloride, starch, sugar, vanillin, Vaseline, and vegetable oil. And you would do this. Dr. White's sad, because you'd have fun doing this. Well, it's sort of fun. It's fun for me to watch. Oh, one thing I should mention, years ago, I had a compound that we used that the lab manager said, could you stop using this? Because your students are throwing away the glassware because they can't clean it. And it's costing us money to replace it. And what was it? Car wax. When you get car wax on glass in a test tube or beaker, it's hard to get out. So I took it out of the list. All right. Now, in part 3, to have students have some fun, I have the same thing, except we're going to mix 2 different items together, and you're going to see what happens. And those items are baby oil and vegetable oil, baby oil and starch, vegetable oil and starch, vegetable oil and Vaseline, ethanol and vanillin, ethanol, vanillin, and then add some water. And here's the results. You don't have to do it. Thank you, Dr. White. Well, not really thank you. You're missing out on a good thing because of the situation with the virus. And then I have questions at the end. And that's today's lab. Based on that, you would find out are these various things polar or non-polar? Remember, water, polar, light dissolves light. Things that are polar are soluble in polar things. Things that are non-polar are soluble in non-polar things. And 99% of the times, if you mix the two together, they're not soluble. If you don't believe me, take some oil and vegetable water and vegetable oil, put it in a container, shake it up, and watch what happens. I'm not going to give that away. With that, I'm done for today. Today's lab day, since I'm on track. And if we were in the lab, this is a quick lab. Most people are done by about 2:30-ish anyways, 20 to 3. So I can say, don't forget, tonight I have my office hours, and if you need any help, come on by. Also, don't forget, hand in the lab that's due today. Keep up. And if you want, send me as soon as possible. If you're going to do the extra credit, email it to me, and I'll check it and talk to you or email back what things you have to correct. That way you can get your 10 bonus points. Remember, it's optional, but who doesn't want 10 more points added to their total? I would if I were a student. And with that, I'll say my world famous goodbye. Gang gesund, goodbye, and have a nice rest of the week and weekend. I'll see you on Monday.